All right, so with this chapter, at the heart of not only this chapter, but of chemistry, section 12.2, stoichiometry. All stoichiometry is a fancy word for saying is we are going to continue doing those conversions just like we did with the chemical mole, but we're going to incorporate the balanced chemical equation. So it kind of merges why we balanced those chemical equations and the info that we learned about the chemical mole last chapter and the chapter prior to that. It's because now we can use that as a tool, as a conversion factor to be able to convert from one item to another, and it helps us predict how many reactants or how much reaction we're going to get. And it also helps determine, hey, if I start out with this many grams of this reactant, I should react it with this number of grams of the other reactant, so you don't waste anything there. Okay, so a really big prediction tool. Yes.
Do you have an extra notes?
Yes, absolutely. They are right up here. Alrighty, so any questions over any of this? We just caught up. Anybody still need it? All right, so moving on here. We're going to do three examples only. We start with the simple and we'll move to the complex. And really when I say complex, it's just going to involve multiple conversions in one single problem. Simplest is going to be a multiple conversions. It's a single step. We go from moles of one substance to moles of another. We add in a little bit more complications with another conversion, and that's where we get our mole to mass conversion. Okay, so we'll start out given moles. We say, hey, find the number of grams or find the mass in grams of this specific substance. And then we'll use our final one. I'll call it the most complex just because it involves three different conversions. You start out grams of an initial substance and you end with grams of your substance that's in the problem. Okay. Notice how both of these that involve your grams, your mass, have to involve the molar mass. Now, from here on, if you need the molar mass, you've shown me that in previous problems and tests and things like that, I'm going to provide you that molar mass. All right, kind of help speed things along. So, questions over this? Anybody need it? All right, so starting with our simplest and then moving to our most complex. Okay, so we'll talk about some steps and then we'll move to an example. Multiple conversions. Number one, every single equation, every single problem, we're going to start the same. Balance, balance, balance the chemical equation. Okay? You got to write down what's given. And then a major thing. Last chapter I said, hey, make sure you go to the middleman moles. And the same thing is occurring right here. You have to convert to that middleman moles or else you can't make this work. Now, you can only convert from one substance to another by going moles of that original substance to moles of the substance that you desire. Okay? Questions? Does anybody need this? Good. All right, so first things first, we got to balance the equation. I'm not even going to read it. I want to balance it. So we start out here and we say this, okay? Carbon on our left, we have three of them. On our right, we only have one with CO2. So what number needs to go in front of CO2? 3. 3 needs to go in front of our CO2. H's, on the left, we have 8. On the right, we only have 2. So what times 2 would get us to 8? 4. Okay, 4. And then oxygens. That's going to be our problem element here. We got 2 on the left. Not really too worried about that. but be careful on the right. We have 3 times 2, which is how many? 6 plus an additional 4 from H2O. So 6 plus 4 is 10. Now we go back to O2. What times 2 is 10? Okay, and we are now balanced. Okay, so now it talks about propane. It's used in gas grills. And we get down to the final sentence here. It says, how many moles of carbon dioxide are produced when 10 moles of propane are burned in excess oxygen of that gas grill? So we're going to start out and we're going to have 10 moles of our particular propane. Okay, propane has the formula C3H8. So we start out 10 moles of C3H8. And the really key thing to this is we say, all right, times, we draw our line, we take out the knife hand, and what unit has to cancel diagonal? Moles. Now, we got to start being careful here. We got to not only put moles, but moles of the substance, which is C3H8. If we're in moles of that substance, we are allowed to convert to moles of anything else in the equation. So we can go ahead and put moles. We desire our carbon dioxide. That's what we want. So we're going to put CO2 up top. Now, where we get those numbers, if we have mole over mole, we just turn to the coefficients in our problem. So we look back, C3H8. I realize nothing's in front, but what number do we assume was C3H8? 1. That coefficient will go right next to the moles of C3H8. Over here on the right, we're trying to get to CO2. What's the coefficient in front of CO2 in our equation? 3. So we're going to put 3 in our value here. Now, this is pretty simple. We take 10 times 3, which is 30. We would divide it by 1, doesn't change our number. So we end up with 30 moles of our CO2. Okay. Questions? Does anybody need this? Okay. Gonna ramp it up a little bit, get our mole to mass a little bit harder because we have our additional conversions. So again, a little bit more complications, add a little bit more steps to this. Key to all of this is balancing the chemical equation, right? You're going to write this down quite a bit. Balance the chemical equation. Write down what you have and get, and you have to cancel your units diagonal. That is key to all of this, right? And you can only convert one substance to another via moles of that substance to moles of the other substance. Questions on this? Does anybody need it? All right. So here we go on this. We got sodium chlorine gas producing sodium chloride. So here's what we do. We got to balance the equation. We start out, we got one sodium on the left, one on the right. So we're good. Cl, though, we have 2 on the left, but how many do we have on the right? 1. So what needs to go in front of NaCl? 2. Coefficient of 2. Right? What did that do to our NAs? 2 of them. So we got to backtrack and say, hey, we need this. This problem, it says determine the mass of sodium chloride or table salt, sodium NaCl, produced when you have 1.25 moles of chlorine gas. So we're going to take this 1.25 moles of chlorine gas, and that's going to be our starting value here. So 1.25 moles of our Cl2. We say times, and we draw our line. What unit has to be down and diagonal? Moles of Cl2. Now, we're already in moles, so we can convert to anything else as long as we convert first to moles moles of that substance. In this case, we want our NaCl, so we're going to put NaCl. Mole over mole, we got to look at the balanced chemical equation. So we'll start here with Cl2. Nothing's listed, but we assume in front of Cl2 we have the coefficient of what? 1. For NaCl, what number is in front of NaCl? And we're not quite done yet because we are only in moles of NaCl. So we say, hey, times, we draw our line. Now what unit has to cancel? Mole of NaCl. Well, we want grams of NaCl, the mass, and it's okay to do that because we're sticking with the same substance. Our last thing that we need to identify is this. Sodium chloride's molar mass is 58.44 grams per mole. That 58.44, is that going to go with G for grams on top or moles on bottom? Going to go with grams. The big number here goes with grams, so we'd have 58.44 grams to 1 mole. All right, so in my calculator, what I'm going to do for this problem, we have 1.25 times 2. I get 2.5. Then the last thing that I need to do in this problem is I say times 58.44, and I get a value of 146.1 grams of NaCl. Now, I didn't divide by 1 because that's not going to change my value in my calculator here. Any questions? Does anybody need this? Alrighty. One final set of directions, one final problem here. It looks like a lot of steps, but it's just adding one additional conversion. It takes us about 15, 20 extra seconds. Again, you got to balance the chemical equation. That is our starting position in all of these problems. Okay? Write down what's given and then start taking that knife hand out and canceling diagonally. Okay? With our items to remember here, we're going to start in grams of that given substance. I've said it over and over again. You cannot do anything. You cannot do anything unless you're in that middleman moles. And so, got to convert to middleman moles. We convert to the substance that we want, and then we convert it back to grams of that substance that we want. Right? 3 conversions. Okay. So again, I call it most complex, but it's just because it involves the most steps. Questions? Does anybody need this? Okay. All right. We got ammonium nitrate, NH4NO3. It's a fertilizer. We know how to determine the mass of water produced from the decomposition of 25 grams of ammonium nitrate. Turn to our equation. So we got to balance it. First thing, be careful. Ammonium nitrate, we actually have one N from the NH4 and another N from the NO3. So we have 2 on the left. How many N's do we have on the right? 2. So our nitrogens are balanced. Hydrogen, we have 4 on the left, but we only have 2 on the right. So what needs to go in front of H2O? Okay, so we put 2 in front of H2O. And then oxygens, we have 3 on the left from that NO3. And be careful, we have 1 from N2O and an additional 2 because of that 2 in front of H2O. So we're balanced, right? We then start out with 25 grams of ammonium nitrate, okay? We start, and I would start way on the left here of your page. We have 25.0 grams of NH4NO3. We say times, we draw our line. What unit has to be down and diagonal? Grams of ammonium nitrate. Now, we have to go, if we're not in that middleman moles, we got to go moles of the specific substance. So we're going to put mole NH4NO3. We see G and mole on top, so we got to use the molar mass. Molar mass of ammonium nitrate is 80.04 number. That number is attached with G for gram. So in this case, that 80.04, is it going to go on top or on bottom of this conversion? It's going to go on bottom with G for gram. So we have 80.04 grams to 1 mole. All right, that's conversion 1 of 3. We keep going. We then say, all right, times, we draw our line. Now, what unit cancels down in diagonal? We're going to get moles of our ammonium nitrate here, NH4NO3. And because we're in moles, we can convert to any substance, but it has to go moles to moles. We want to go to water, so we're going to put H2O. Now, question for you, mole over mole, where are we going to turn to find those values? Coefficients. On bottom with NH4NO3, nothing's written, but we assume that's what number? 1. So we say 1 in that number there. On top, H2O, what coefficient is in front of H2O? 2. And we're not quite done yet because we want mass. We want the number of grams of water vapor. So we got to do one more conversions. And so what we do is we say, hey, times, we say times, draw our line now. What unit cancels that down diagonal? Yep, moles of water. Because we're with moles, we can put our G for grams up top. The molar mass of water is 18.02 grams per mole. So this 18.02 number, does it go on top or bottom of this final conversion? Top. So we have 18.02 to 1 mole, and we turn to our calculators. Now, there's 3 conversions, okay? Not too worried about the dividing by 1, but here's how I do this. I say 25.0 divided by 80.04. I press enter, and I get 0.3123. Number keeps going out. Then, next number of importance is this 2 on top, so I keep that number in the calculator. I say times 2. Press enter, I get 0.6246. Number keeps going. Last thing that I do is I multiply by 18.02, and when I do this, we round to 1 decimal in this case here. What is our mass of water? Yep, 11.3 grams of our H2O. Okay. Questions? All right.